Thank you very much for that introduction, Ann. As you said, my name is Eric Com. I am with a software company called ESI, and we're going to be talking about IC.IDO. It's an engineering virtual prototyping software that has enabled our customers to bring their products out of the digital world, out of the CAD tubes, and into an immersive, experience-based virtual reality so that they can evaluate whether or not their products are, in fact, producible, well integrated, and also serviceable and maintainable while out in the field. So take, for example, if you had a product like this. In the background, you can see that is a Bombardier train. That is the Talent 2 model train from Bombardier. And these days, because of the successes with virtual design, computer-aided engineering, finite element analysis, we've effectively done away with the need for virtual or for practical prototypes. People don't build prototypes anymore as part of the engineering development process. They only build prototypes these days in order to validate and approve final designs. But we don't have the flexibility and freedom to build a physical mock-up in order to instruct and illuminate and educate us about the engineering process. And that also has left room for more risk in our engineering designs. Because quite often, if you're doing a computer-aided design, you design all your products in the finished position. All of your CAD bodies, all of your math data starts in the finished position. And sometimes engineers and designers don't actually do the diligence to be able to envision how do the products make their way from the manufacturing facility where the parts and components are manufactured, and how do they get put together to make this end product. And unless you actually do the prototyping process, the piloting process, people don't have the opportunity to accidentally discover the unknown unknowns. And so this is about how it's useful to bring a CAD model into the VR environment so you can do a virtual build, virtual integration, and virtual service scenario of your new design product. So one of the first things that makes virtual reality and the way we do virtual reality very important is locality. As an engineer, I'm sitting there at my desk, I'm sitting there in my cubicle, and I'm designing maybe that massive product of the entire train. I don't have the time or the flexibility to leave my workplace, march myself over to the piloting facility, and see what the prototype's looking like. I need to be able to see and experience that train from the ease of my own desk, the ease of my own office. So I want to localize, I want to make it possible for people to be able to get to their virtual model. So locality is a very important aspect of why virtual reality matters in engineering environments. But another aspect is simplicity. We don't want to have to create all sorts of additional workflows in order for me to validate my engineering design. One of the terrible things we hear from people these days is they say in order for them to bring their CAD designs into VR, they take it into some sort of middleware, they rinse it through the middleware, reducing polygon counts, reducing product complexity, and then they bring it into VR and try to see whether or not it's possible to put the thing together. But there's always a possibility that in simplifying their CAD data model, they accidentally simplify out the thing that they were actually looking for in the VR as far as the good or bad aspects of their design. And this was a word that my colleague who did this presentation originally put up there. I believe it's temporality, right? Time basis. These engineering models that we're creating, these VR virtual prototypes, quite often, they're only used maybe once, twice, maybe 3 times in their lifetime before we make a new engineering decision, which drives new CAD data, which drives new VR experience. So just around the corner here in the NVIDIA booth, I've been showing people the actual CAD data of that Talent 2 train. I've used that Talent 2 train model more today than our customers at Bombardier use that CAD model, that VR model themselves. Because when they load it, they use it to find engineering decisions to inform their next design decision. And as soon as they make a new decision, that experience is not useful anymore. They have to make new CAD data and bring that new CAD data in. So the temporality of VR when you use it in engineering means I don't have the time to rinse it through some other third-party product to simplify it, to scrub pixels and do things like that. And I don't want to open up the possibility that I spend so much time on the CAD model that I just want it to work instead of finding out that it actually does or does not work. So here's the data set that we were talking about. This is an entire Bombardier train. This is 200,000 nodes, so that's 200,000 individual CAD objects. Some of them are engineered and designed by Bombardier themselves. Some of them are supplied components that they're getting from their vendors. And they integrate all those different CAD models together into a single VR experience. That's somewhere in the ballpark of 155 million polygons that we wanted to explore and evaluate in VR. Now, in VR, we wanted to make a new step and do it in VR on a HMD. So Bombardier is a longtime customer of ours at IC.IDO. They've been using us predominantly in a power wall, in a projected VR cave environment. But what they saw as opportunity to make this a bit more of an in-process review, if only an engineer could see his whole train on an HMD. But this raised a couple challenges when you think about the size and the complexity of this train. So what I'm going to do is I'm going to walk you through a little progressive history of how we've been working hand in hand with NVIDIA, leveraging their SDK, NVPro pipeline, and also VRWorks and DesignWorks in order to optimize our solution to help our customers out. So rolling back the clock a little bit, back to the Kepler class GPUs. Back then, in order to load that entire train into the VR model, we could only achieve a frame rate of about 2 frames per second, right? That meant that in order to see something at a reasonable frame rate, 90 frames per second, in order to be a good experience on an HTC Vive or an Oculus Rift, we would have to actually reduce that model to only 1.8% of the complexity or the size or the objects in that model, which means I'm not really discovering the problems inherent in that train design. If I'm always carrying around the simplified model of the train, I'm not seeing the big picture problems. I'm just seeing the problems that I knew to look for when I was doing the data simplification, right? So this is kind of human-based culling of the data, simplification of the data. Well, things get a little bit better as the Kepler class was replaced by the Maxwell class GPUs, and we saw that some of our other models were able to achieve better and higher frame rates inside of our VR rendering tool. So at the very top, we have Model B. That was a model on the ballpark of somewhere around 15 to 20 million polygons, and we saw that going from the Kepler to Maxwell did in fact give us an improved overall frame rate. When we went to that Model C, that black dashed line, that was a model somewhere around the order of 25 to 30 million polygons. A little bit of an improvement, but not a huge improvement. With the 150 million polygons of the train, it almost looks like a perfectly horizontal line from the Kepler to the Maxwell. So we still had a little bit more work to do as far as bringing these large models to an HMD. So back in 2016, last year at the GTC, my colleague Andreas Monk, out of our visualization team, presented a paper in working together with the NVIDIA DesignWorks folks on how to improve our overall rendering pipeline. And so when we went from the old rendering pipeline to the new NVPro powered pipeline, that allowed us to, across the board on all the different architectures of GPUs, to improve our overall performance 5 to 10-fold overall for frame rates. So that meant that 2 frames per second was now going up to 5, 10, and 13 frames per second. And that meant that now with NVPro pipeline, we could see almost 15% of the train, which is still a little bit disappointing, right? So this would have meant that any one of those Bombardier engineers who's trying to troubleshoot his engineering design, trying to troubleshoot how that train goes together, would still have to very much eliminate 85% of the train in order for them to solve their particular problems. Maybe that would be good on a subsystem or component level, but it still wouldn't help them integrate their components to the larger environment, to the larger train. So then in working with NVIDIA a bit more comes the VRWorks SDK. We leveraged the VRWorks SDK with our latest version of our commercial software, and in doing so, we were able to leverage VRSLI, and that meant that we could now take 2 graphics cards and have 2 graphics cards split up, divide and conquer that work of rendering the left eye and the right eye. And that overall brought us a very significant improvement because that meant each GPU is now only rendering 1 mono image. That got us up to 21 frames per second. So that meant just shy of 25%. 1/4 of the train could we look at any one time. That still meant that we weren't quite ready to be able to look at these large data sets on an HMD. When this version came out in the fall of last year, and that meant we could tell our customers at Volkswagen, you guys can load an entire car as long as you're using 2 GPUs, because an entire car was somewhere around 50 million polygons, right? So 50 million polygons was sufficiently small that we could get it all working on an HMD with acceptable frame rate. But our customer over at Bombardier is going, what about us? Our customers over at Boeing going, what about us? Our Marine customers are going, what about us? We still want to see our models on an HMD. So another improvement with the latest cards is just migrating from a Maxwell card to a Pascal card. We saw another improvement in overall rendering performance. This was also with the VRSLI. We could now get up to 35% of the train, 33 frames per second. This bought us a few 10 million more polygons overall, so that Volkswagen Group could now say, oh, the MAN truck division will be very happy. Volvo Truck was happy, but Bombardier was still feeling a little bit left out in the cold. So then comes another innovation from NVIDIA, another toolkit for us to leverage from the VRWorks SDK, which is single pass stereo. Single pass stereo is another thing that came along with the package of moving from the Maxwell to the Pascal class GPU. With single pass stereo, now that meant we could take that single GPU and we could have that in a single pass rendering that left eye and that right eye. And that bought us another... That's not much of a performance increase, is that? Right? When I was in VRSLI, I was running at roughly 32 frames per second. And now I'm on single pass stereo and I'm still at 32 frames per second, but that's with a single GPU. I know, I'm sorry about that, guys. We're selling 1 fewer GPU per installation of IC.IDO. But what that meant is that now we did make the overall cost of ownership of doing this kind of VR work in our tools a little bit more achievable. That a single workstation with a single P6000 graphics card was able to achieve 33 frames per second of that 150 million polygon model, which meant the guys who had the 50 million polygon model could buy just 1 GPU instead of 2, or that engineering group could have 2 workstations instead of just 1. And that really meant that we could really move a lot of this VR workflow away from just being that final validation, final approval gate review, but now that could be at the desk, at the workstation of any engineer who has critical decisions about how their components, how their systems integrate with other products during the process of assembly or disassembly, and how people on a one-to-one interactive way participate with their designs. Because when we talk about VR in our environment, we really want to make it such that our customers are able to not just view their designs in stereo, but we want them to interact with it on a one-to-one scale, full-scale realism, so that inside of our environment, now there's a kinematic mechanism on the front of that train. We can simulate in real time that kinematic mechanism and have a person in VR grab that kinematic mechanism and swing it back and forth, have it translate in and out with the natural mechanism's movement, and see whether or not those hoses and wires that come out of that mechanism were pinching or binding at any range of the motion. But Bombardier still couldn't quite get their entire model into an HMD yet. So most recently at, again, GTC last year and also Siggraph' a few years ago, we were talking about how could we get even more rendering performance out of a GPU. And the most recent innovation was with occlusion culling. With occlusion culling, combined with the single pass stereo, combined with the improvements that we have from the NV Pro pipeline, we were now able to get that 150 plus million polygon model to render at a frame rate in excess of 90 frames per second. And that meant that the typical user sitting at their desk could strap on an HTC Vive, strap on their Oculus Rift, and they could solve engineering problems on real CAD data, unculled manually, unoptimized, no pixel scrubbing, no triangle optimization. Just bring the CAD data natively in, import it, look at it in an HMD. Then actually participate and simulate that in real time. Right? So this has been a huge step forward for Bombardier, because Bombardier, up until that point, they would always have to load up their full engineering designs on clusters of computers, on practical render farms attached to only projection-based cave environments or power wall environments for doing their virtual reality views. Now, that was really good for the engineering bigwigs, the VIPs, the customer to come in and participate. But the rank and file engineer doesn't have a cave or a power wall at their disposal, and they're not able to integrate that into their daily workflow. But now with this capability, they'll be able to use it day to day at the point of decision. So as soon as I make a new decision about how that train should fit together, about a new mechanism that I want for the doors, a new mechanism for how the individual cars hinge together, I could actually evaluate that myself on my workstation with an HMD. And so here's just a couple examples of just how the occlusion culling really improved our overall performance. I load the entire train model, 150 million plus polygons, 200,000 CAD objects. But when I zoom in and I'm looking at just the wheel mechanism, that's called a bogie, I've been informed by the people in the train industry. That bogie underneath the train, when I'm looking at just that, my frame rate performance is through the roof. I'm getting all kinds of really good frame rate, really good performance, because I'm not looking at maybe 1% of the overall train when I'm looking at that area. When I zoom back out and I see the entire train, yes, my frame rate's going to drop down to something in the 90s, but still a very high fidelity experience for our customers, because we're not playing video games here. We're exploring our data, we're opening it, we're closing it to make engineering decisions. So these kinds of performance numbers are, while not 100% typical, they can be expected for a complete model like this. So now anybody who's engineering anything smaller than a 1, 2, 3, 4, 5, 6 compartment train, they can load their entire model onto a single workstation, single Pascal graphics card, and be able to look at it on an HTC or an Oculus Rift.